Hello, I didn't see you there. I was just out here going for a nice stroll in the beautiful outdoors. You know, while we're out here, why don't we do some hydraulics? This little creek in my backyard in Sellersburg, Indiana is known as the Anson Branch. The Anson Branch is a tributary to the Muddy Fork, which feeds into Silver Creek, which, believe it or not, feeds into the mighty Ohio River. Now, the first thing I like to do with a stream like this is determine if the flow is supercritical or subcritical. And we're going to do that by using Professor Troy's splash test. Let's get into it. So where we are right now, the water is flowing from left to right. As we splash in the water, we see that we're sending ripples upstream. This tells us that the flow is subcritical. However, there are also some shallower parts of the stream, and here we can't send any ripples upstream, so we know that the flow is supercritical. We are also able to observe some hydraulic jumps where the water is forced up by rocks. Now let's see if we can't get a good estimate for flow rate. Now we all know the equation for flow rate. Q equals VA. Let's start with V, velocity. Back behind me here, I've marked off a 15-foot length of the creek. What I'm going to do is allow an object to float down this 15-foot length and time how long it takes. Knowing the distance, 15 feet, and the time, I can find the velocity. To ensure accuracy on this, I'm going to do multiple trials with multiple different objects. Now, let's talk about A, area. Now I picked a length of the creek that has a fairly constant width as well as a pretty uniform depth. This is to ensure the most accurate calculations for area. While collecting data for velocities, I used 3 different objects: a stick, a piece of bark, and a leaf. I tested each object 3 times. Taking measurements for area was a little more tricky, but after I overcame some of the physical barriers, I was able to settle on some numbers. Well, now that my feet are wet, I think it's time to head back to the lab so we can analyze some of this data. After running some of the numbers, I came up with a flow rate of 1.67 cubic feet per second. I then used Manning's equation to calculate the uniform flow depth. For the slope in the Manning's equation, I used 4 times 10 to the negative 4th, which is the number that they give us on problem 2 of homework 10. After running through several iterations of Manning's equation, I found 0.35 feet to be the uniform flow depth. Now, this is lower than the measured depth that I have of 0.67 feet. Given that the flow is subcritical, that puts us on the M1 slope shown here. Thank you all for joining me on this adventure. If you're interested, please check out my write-up for more detailed findings. See ya!